In this video, we will be looking at polynomial functions that are going to extend beyond quadratics, which we were talking about in the last section. Our goal is to be able to understand what the graphs look like just by looking at the original function, knowing how the extreme ends of the function will behave, whether they're going up to positive infinity or down to negative infinity. We want to be able to factor polynomials of higher degree so that we can find the x-intercepts or the zeros and understand what happens when those x-intercepts potentially are repeated. The word for that is multiplicities. A polynomial function is one that has this generic format. It's written with x raised to a particular power as the variable. You can see that we always write polynomials in order from the highest power. In this case, we're just saying generically x to the n power. And then the next variable would be x to the n minus 1 power, meaning that the degree of that variable has been reduced by 1, and so forth, going down 2 at that point and down to when we have x to the first power. And then our last term doesn't have a variable at all, but we could kind of think of that as though we have x to the 0 power. Anything raised to the 0 power is 1, so we don't typically write the variable with that last term. That last term is a constant, right? Just a number. You can see that all of the coefficients in front of the variables have this numbering convention. We've labeled a sub n, meaning that there's a subscript that the number is written just below it. The variable, or sorry, the number n is going to match with the exponent. So I might have an example would be 5x to the third power and 8x squared, 12x to the first power plus 7. We would say that the number 5 is a sub 3. It's the variable that is associated with x to the third power. We would say that 8 is a sub 2. It's the coefficient. I don't know what I said before. I meant that 5 and 8 are the coefficients that are associated with the variable raised to a particular power. And the very last one, like I said, the constant, because it'll just be a number, that would be the same as this. This is a naught or a sub 0, a sub 0, or a naught, meaning that it's as a 0 term that's there is the constant. All right, one of the key components of the definition is that all of the coefficients are going to be real numbers, so they can be decimals or fractions, and then the exponents are always going to be whole numbers. All of the graphs of polynomials will be smooth functions that don't have any discontinuities. There won't be any holes, there won't be any corners like on an absolute value graph, and the domain of these functions will be all real numbers. If the degree of a polynomial is 0, we have what's called a constant function. We could write this as 4x to the 0 power. We don't usually write that, we would just write 4. And so the graph of that is going to be a line at 4, right? This would be the same as y equals 4, so that's why we call it a constant function. When the highest degree of polynomial is raised to the first power, it's a linear function. It's going to be a straight line. In the last chapter, we talked about things that are raised to the second power being quadratics. And then we have cubics and quartics and things going up. We would just say x to the fifth power or sixth power, a degree 6 polynomial, for example, as we move into higher powers. Just a little review as far as quadratic functions are concerned. If we factor a given quadratic function, we are able to assess from that what the zeros are, or the x-intercepts, right? Those two things are related to one another. What we're really doing in that case is we're setting the original equation, f of x equal to 0, and then solving. The y-intercept is going to come from when we let x equal 0. And when we plug x into the original, the first terms will go away, and we'll just be left with that constant term. So the y-intercept is going to end up being that last number that's by itself, 0, -3. We talked in the last section about how to find where in this case, minimum is, because the parabola is facing up. We said that that would occur at x equals -b over 2a. In this case, that would be -2 over 2 times, negative, right? So this changes to positive 2 times 1, which is 1. The domain is all real numbers. That's going to be true for all polynomials. And the range is going from that minimum point. The minimum point was found by taking that axis of symmetry number, and if we plug that into the original, 1 squared minus 2 times 1 minus 3, we get that f of 1 is -4. And so that's how we're getting the other coordinate, and we know that the minimum is at -4. So that helps us know that the range is going to go from -4 all the way up to positive infinity for this graph. Again, this is a review from the last section. When we have a cubic function, you can see that this is a little bit more complex. One of the main things to notice is that in the polynomial that's raised to the second power, we ended up having 2 zeros, or 2 x-intercepts. When we go to this one that's raised to the third power, we end up having 3 zeros, and you can see that we have 3 x-intercepts. The process to find those zeros is similar to what we did in the last example. We factor the given function, and when we set that equation equal to 0, we're able to extract the 3 zeros, -4 for the first one, -1 for the second, and 3 for the third. We find the y-intercept the same way. We let x equal 0, and so that number at the end ends up being the y-intercept. Now this part is sort of involving calculus a little bit, maybe looking at some graphing software or a table, because we really don't have a good way at this point to know how to find this relative max and relative min. What we mean by relative maximum, that would be right here, is it acts like a maximum just sort of in that area, but we know that it's not a maximum for the function overall because there are points over here that are higher than that one, right? And similarly, we would say that this point here is a relative minimum. It acts like a minimum just sort of in the neighborhood around where it is, but it's clearly not the lowest value for the whole function. There are values over here that are lower than that one. Part of calculus is helping you determine how to find what those relative max and minimum points will be. We can see by looking at the graph that the domain and the range for this are going to be all real numbers. As a reminder, one of the ways to factor things like this when you have 4 terms is to use factor by grouping. Here are some examples of polynomial functions. As we stated before, something that is squared or a quadratic is going to look like a parabola. Anything where we've got the variable x, this is like -3x to the 0 power. When something's raised to the 0 power, that's a constant function. This is a quadratic. A cubic is going to look like this. One of the sides is going to be going to positive infinity, and one of the sides is going down to negative infinity. And then here we've got something to the fourth power. And it's got some interesting little changes in it. Parts of it, like way at the extremes, it looks sort of like a parabola, right? A parabola turned upside down. It kind of makes sense that it's turned upside down because there's a negative in front of the leading term there. We'll talk about how to know what the general shape of a graph looks like based on the highest power on the variable or the degree of the polynomial. These are examples that would not be polynomials. An absolute value. This is not polynomial because it's not smooth. It has a cusp, or in this case it's called a corner, when you've got two straight lines that meet each other. A cusp is one where you've got two things that are curves that meet at what looks like a corner. This is this one's not a polynomial because it has something raised to a fraction, the square root one. We could write this as x plus 1 raised to the 1/2 power. Remember that when you take the square root of something, it's the same as raising it to the 1/2 power. When we have fractional exponents like that, those are not considered to be polynomials. And then here we have a rational, right? And we can see by looking at the graph that it's disjoint, so that's also not a polynomial. All right, I was sort of alluding to this just a slide or two ago, where if we look at the leading term, the very first term of a polynomial, that tells us what's happening at the ends of a polynomial. So when the highest degree is even, then that means that we're either going to have both sides facing up or both sides facing down. So examples of that would be if we have x squared, we know that in general the graph is going to look like this. If we have negative x squared, then the graph is going to look like this. That'll be exactly the same for, let's say, x to the fourth. X to the fourth is also going to look similar to x squared. And negative x to the fourth, is going to look similar to negative x squared. There's this notation that they have written here as x goes to infinity or as x goes to negative infinity. The way that we're talking about this is we're talking about what's happening on the x and the y axis. So let's suppose that I draw an axis system here. As I move in the direction of positive x, that would be going this way, right? What's happening to the y values? As x goes towards positive infinity, y is also going towards positive infinity. On the flip side, as I move in the direction of x towards negative infinity, as x moves towards negative infinity, what's happening with the y values? Y is going to positive infinity. This is the way that we typically will write a description of the end behavior. We're talking about what happens way at the extremes of a graph, right? Let's look at this one over here. Looking at this graph here, and I'll make an axis system. As x goes towards positive infinity, y is going towards negative infinity. I'm saying that as I move this way in the x direction of x, the graph is going down towards negative infinity. Going the other direction, as x moves towards negative infinity, so as x goes this way, what's happening to the graph? Y is going towards negative infinity. Again, this is a way that we describe the end behavior. For odd graphs, like the x cubed graph or x to the 5th graph or x to the 7th graph, right? X cubed, x to the 5th, x to the 7th, and so on. The end behavior is in the opposite way. As x goes to positive infinity, y is going to positive infinity. And as x goes towards negative infinity, y is going towards negative infinity. Notice that this is what happens when the very first term is positive versus when the very first term is negative, and that would be a reflection over the x-axis. So when I look at this graph, it's got the opposite end behavior as this graph because that negative sign reflects the graph over the x-axis. All right, in this slide, we're just doing a little bit of matching. Anything that is raised to an even power, like a and d, they are going to follow the same kind of guidelines as a parabola. This looks like it's going to be even, and it's going to be positive because it's facing up, whereas this is also going to be even, but it's going to be negative because it's facing down. I know that it's even, an even power, because both of the endpoints are facing in the same direction. So looking at the two that I've highlighted, I think that this one is going to be letter D, and this one is going to be letter A. Right? So this is the one that's 3x to the 4th, and this one is negative x to the 6th. Looking at the other two graphs, B and C, they're both odd. And with odd functions, the graph is going to have one side going up to positive infinity, one side going down to negative infinity. The standard way that we see those graphs is here. This is going to be an odd function, and it's going to be positive. Positive meaning the very first coefficient in front of the whole function. This is going to be odd, but it's going to be negative because it's flipped upside down. So looking at the two graphs that I have, I think that this one is going to be letter C, the one that's x to the 5th, because it's positive in front. And this one is going to be letter B with the negative 5x cubed. That negative in front is what flips the graph upside down. We will talk a little bit about some of the advanced techniques to factor polynomials. But when we have a polynomial factored completely, it helps us determine what the zeros are. Now, I can see from this polynomial, because there are 4 different factors, this would have been something that had an x to the 4th power. I've got 4 x's there, and then there's a 5 in front of it, right? So based on what we were just talking about in the last slide, I can see that the end behavior, it's an even function, so both of the ends will be facing the same direction. And this number 5 is positive, so they're both facing up. So that graph kind of makes sense to me. But one thing to notice is that some of the zeros are repeated. We have 4 zeros, but the 0 at x equals 2 shows up 3 separate times, right? And so one thing to notice about the graph is that where the zeros are, here's -1, right? And then here is +2. I don't show that the graph is crossing the x-axis 4 times, even though this polynomial was raised to the 4th power. Notice that when the degree is odd on a factor, like this one is to the 1st power, the graph travels through the x-axis. This is also odd, and the graph is traveling through the x-axis. It looks kind of like an x cubed graph in this region, right? And that's because this is raised to the 3rd power. Let me see if I have another example. When we have something that has an even, this is called a multiplicity, it will act like a parabola. So let's suppose that I had f of x equals x minus 2 squared and x plus 1. Just taking that same function we had before, but modifying it slightly. This would have been something that had x to the third power, right? Because I have two x's in this first factor and then one in the second factor. What will happen in this particular graph is that at -1, I'm still going to go through the graph, but at +2, the graph is actually going to sit on the x-axis. So the way that this graph is going to look, it's going to look like this. It's going to come down here. Oops, go back. Hang on one second. What's going to happen with this graph is it's going to go up through one of the zeros at -1, and then when it comes back down to where the variable, or sorry, the zero is at +2, it's actually going to sit on the axis because of this squared term. And so it acts like a parabola when the exponent on the multiplicity is an even number. If it's odd, it'll go through. This is what this slide is saying. If the multiplicity, meaning the power on the factor, if the multiplicity is odd, then the graph is going to cross through at that particular zero. So it'll go like this. This would be for an odd exponent. If the multiplicity is even, then it's going to be tangent or sitting on the x-axis. That can come in a couple different ways. It could be that it's facing up. It could also be that it's facing down. So for an even exponent, the graph is going to sit like this. Right? It could have other things that are happening, but right at that particular point, it's just going to sit right at, right on top of the axis. Here's an example of a cubic. We factor by grouping this. We took out of the first two terms an x squared. And out of the second two terms, we took out a -9. And then putting this all together, we have x plus 2, x minus 2, x plus 3, x minus 3, and we get 3 zeros. We're always expecting to get the number of zeros that will match the highest degree, the highest power or the degree, but that could include multiplicities. For a number, for this one, which is raised to the 4th power, the way to think about factoring this is to actually make a variable substitution. Let's let x squared equal m. So then x to the 4th power is m squared. So I could rewrite this as m squared plus 4m minus 45. That's m minus 5 and m plus 9. Or going back and plugging in our original variable exchange, we get that x squared minus 5 x squared plus 9. And then solving those two equations for equaling 0, we get x is plus or minus square root of 5, or x is plus or minus 3i. So again, we're getting 4 possible solutions or zeros because the original was raised to the 4th power. Now we know that only 2 of them are going to end up being x-intercepts, right? Because those are real numbers. These are not going to be part of the graph. So kind of putting all this together, the number of zeros is going to be at every polynomial will have at least 1 0, and they should have exactly whatever the highest power is but that's also including multiplicities, right? You can have one of the zeros be repeated. In this example, we're looking at a complex polynomial that is estimating the number of milligrams of pain relief medication in the bloodstream T hours after 400 milligrams of the medication is taken. You can see that looking at the graph that there's an increase up to about 2 hours. It looks like about 2 hours after taking the medication, the amount of pain relief is probably at its maximum, and then it sort of tapers off to the 6-hour point. In this particular example, they just plugged in a number of various points, 0, 0.5, 1, just to kind of get a rough sketch of the graph. In our class, though, we'll be using Desmos to get a graph like this, so you don't need to really worry about plugging all of these individual points into a calculator. All right, that's all for this section. Look for the next video, which is going to give more specifics about polynomials. Have a great day.